I guess you can argue for.
Well, wait a minute. Well, if it's not stationary, it could be any process, the jaggedy one.
Oh, so you already know that it's not.
Right. I mean, we have a counterexample. Just take the process.
Oh.
Yeah.
Okay.
Yeah. Okay, let me remind you, next week. All right, first of all, this is Tuesday. And we'll have regular lecture on Thursday. And then next Tuesday will be a double lecture. It goes until 1. And the following Thursday will be a double lecture that goes until 1. And then the week following, there'll be no classes. And then we'll come back for a class and have a midterm Thursday after. Great. And now, I want to look at the entropy of the future given the past. And good. I'm going to throw away Markovity. And I'm just going to look at a stationary process. And I wonder whether the entropy of the future, given the past, increases as the future becomes more and more remote from the past. Well, there's a problem. If I want the entropy of Fn, which is this segment going to infinity, given the past, everything up to time 0, well, what's the entropy of the future? It's infinite. There are a lot of things that can happen at times n, n plus 1, n plus 2, etc. What's the conditional entropy given the past? That's infinite too. So what are we trying to do if we're trying to show a function that's infinite for all n is increasing? So instead what we'll do is we'll look at the mutual information between the present up to time 0 and the future from n to infinity. I call that P0 for the past, Fn for the future. Now, why do I look at mutual information? Well, if I wrote it as the entropy of Fn minus h of Fn given P0, then if I goes down, the entropy goes up, assuming they're all finite. But the conditional entropies aren't finite, but this expression is. It's the difference between two processes between two functions that are going to infinity, but the difference goes to a constant. So I look at the mutual information, I realize that it specializes to a statement about the monotonicity of the entropy. So what we hope to show here is the mutual information between the past and the future decreases, And in addition to decreases is convex. That would imply, in these other cases, the conditional entropy increases and is concave. Now, time to see what does mutual information mean. Mutual information will, especially after we're done with Shannon's second theorem, which we do this quarter, is the resolvability of the inputs that's given by the output. I of x, y is, if you have control of x and I see a fuzzy random version y, I of x, y is essentially the logarithm of the number of distinguishable x's. To make it a crisp theorem, we repeat it many times in space, block length coding, and we get the law of large numbers kicking in, and it becomes a precise statement. In n looks, you can resolve 2 to the n I things, with probability of error arbitrarily close to 0, as n tends to infinity. Okay, so this mutual information has to do with how much information the past has about the future. Look, if I look back a few years ago and I see the history, I can say, oh, I know how hot it was each year and how many animals of each kind there were and so on. If I go back 1,000,000 years, the past is talking to me. It left fossils, it left tectonic plates that South America and Africa apparently fit together and blah, blah, blah. So, yes, but the resolvability of the past, given that it's 1,000,000 years ago, is rather small. And this is a past that's not even trying to signal to us. So it has to do with mutual information and not the maximum mutual information over all possible histories. Now, there is one example of a past that is trying to signal to us, and it's called civilization. With the advent of writing, we took everything we learned in this generation and passed it on to the next and built on it and built on it. We're signaling the future, and so instead of being just a sequence of animals called man, we become mankind, which is a civilization which is immortal, or at least locally in time. I have no idea what's going to happen in the future. These theorems don't speak to that. All right. So, how do you prove this? And this is the last thing we will do today. How do you prove that the mutual information between the past and the future decreases? Alright, I can't reset, so I'll go back over here. I use the chain rule to expand that. Is that all I do? Yeah, I realized that f sub n, the future n, is the same as f sub n minus 1 except for knowledge of the random variable x sub n minus 1. So, I have that, I expand it by the chain rule, one term cancels the other, I get a conditional mutual information, and that's negative, non-negative, non-positive, and so we have the fact that it's decreasing. Now, for the convexity, we go through some more algebra. It's interesting to look at the steps, but I don't think it'd be interesting to go through them right now. And you end up with that not only does the resolvability of the past as viewed by the present decrease, but it decreases more and more slowly. That's what the convexity would tell you. Here's one little thing. You'd say, wait, I know a function that's decreasing. I can stretch time out here and here and here, and it still is decreasing. But if it's decreasing and convex, if I stretch time out, it's still decreasing, but it may no longer be convex. So how can I, in this level of generality, prove that resolvability is convex? Does it tell me something about time? No. It's the reason for it is the minute I assume stationarity, I'm assuming the drumbeat of time. That is, if I shift it this way, it has the same joint distribution. So I don't allow myself those elastic time changes, because that would destroy the stationarity. So that resolves that little paradox. Okay, so that then gives us the tie-in between physics and information theory. And next time we'll start on a new topic.
Make an assumption that the time is discrete.